So go to Zoom, and then
share the screen.
That one. Share. Yeah. I'm going to do that here. Does that look okay? It looks okay here.
Yeah.
Right, so our final speaker of the morning is Prashant Purohit, University of Pennsylvania, and is going to talk about dissipation at a shock wave in an elastic bar.
So thank you. I also must thank the organizers, especially Mark Hofer, for inviting me here. I'm an outsider in the community, and you will notice it in my presentation. My work is mostly in mechanics of solids, and the topic that I'm going to be talking about here is the dissipation at a shock wave in an elastic bar. This is joint work done with Rohan Abhiratne at MIT. Okay, so the problem that we are imagining is a semi-infinite bar, like shown here, and this semi-infinite bar is subjected to an impact. I know when you think of impact, you think of a compressive impact, but for particular types of materials, you can also have a tensile type of an impact like that. And when you perform such an impact experiment on the bar, and the material of the bar is an elastic material that is stiffening, like this, the stress-strain curve is stiffening, then there is a possibility of getting shock waves. And that shock wave manifests itself as a discontinuity here. Behind the discontinuity, there is a finite strain and particle velocity. Ahead of the discontinuity, the strain and particle velocity are equal to 0. Now, at these shock waves, you can get dissipation occurring, and the dissipation can be computed by determining the difference of the work done at the boundary minus the strain energy and kinetic energy stored in the bar. So that's the dissipation that is occurring at this shock wave, and conveniently, it can be written as a local quantity which is in terms of the difference in strains ahead and behind the discontinuity. Okay, so that's the dissipation. And in terms of the graph of the stress-strain curve, it is the difference between these two areas multiplied by the speed of the discontinuity. That's the dissipation rate, okay, even though this is an elastic material. Now, what form does this dissipation take at the microscopic scales? That's the question that we are interested in. This is motivation number 1 for the problem that I'm going to show you. Motivation number 2, and this goes back to my days as a PhD student. At that time, I was working on impact on bars made of phase transforming materials like nitinol. Nitinol is a shape memory material that is used in a number of applications in medicine and many other applications even in space technology these days. At the time, what we were thinking about was simple one-dimensional problems, and the one-dimensional problems were discretized, just like the one that I showed you in the previous slide, as a bunch of masses and springs like that. The energy landscape of these springs had a double well, so it is a nonlinear energy landscape. It's not a quadratic, okay, like it would be for a material that is a linearly elastic material. The stress-strain curve for such a material looks like this. It is up, down, up, and this branch is phase 1, maybe it is the austenite, and this branch is phase 2, maybe it is the martensite. And the martensite and austenite structures at the atomic level are shown here. When you perform an impact experiment on this, what can happen is that if initially all the atoms are in the austenite phase, they can go into the martensite phase through a phase transition. Okay, and I'll show you some examples of integrating that equation of motion for this chain of masses and springs. So that's what, for low velocity impacts, this is what your solution might look like. And here what I'm plotting is the atom number or mass number and the interatomic distance, that is the strain, as a function of position at 2 different times. And what you see here is first there is a sonic wave that goes into the medium, and behind it at a lower speed is the phase transition front. Behind the phase transition front, there is a bunch of oscillations. Okay, That same plot can be also viewed. You choose any particular atom, like atom number 260 or mass number 260 or 280, and you can plot in time what the interatomic distance at that location is, and you get the same thing. That is for low velocity impact. For high velocity impact, again, you see similar structure. There is a sonic wave going in the front. There is a phase transition front going behind it. And behind the phase transition front, you see a bunch of oscillations. That might look to you like a dispersive shock wave because there are modulated oscillations that are decaying away as you go further and further away from that phase transition front. Once again, there is dissipation taking place behind this moving phase transition front, and we want to understand this dissipation more carefully. Okay? We've also solved Riemann problems, just like the previous speaker, and I wanted to flash that slide before you just to show that they give you very similar looking situations where there is a phase boundary propagating and there are sonic waves. This time there are two sonic waves because it's in not a semi-infinite domain, it's an infinite domain. Okay, now in order to understand this problem of dissipation, we are going to solve three problems. Problem one is a continuum problem, and in the continuum problem, we are thinking of a bar like this. The reference position of particles on the bar is labeled by x. The deformed location of particle x at time t is given by y. So once you have yxt, you can compute the strain field, gamma xt, as simply the partial derivative of y with respect to x. Particle velocity is dy dt. And the stress field is some sigma xt, which will be given by a constitutive law. So the equation of motion is simply Newton's second law. Rate of change of momentum is equal to the divergence of stress. The constitutive law is given by some stored energy function, which is a function of gamma alone, gamma the strain. Okay, I'm going to prescribe what that W is in a minute, and the stress simply is the derivative of this W with respect to gamma. Once again, we are interested in solutions in which there is possibly a discontinuity, a propagating discontinuity. The position of the discontinuity in the reference configuration is given by this variable S. Behind the discontinuity, we have some strain and particle velocities labeled by minus. Ahead of the discontinuity, we have strain and particle velocities labeled by plus. And then the standard Rankine-Hugionio type jump conditions can be written down. All this is not news to you. So this is the kinematic jump condition across that discontinuity, written in terms of the jump in particle velocity, jump in strain, speed of the discontinuity. You could have momentum jump conditions coming from Newton's second law, and that involves the jump in stress and the particle velocities. Very good. Dissipation in an elastic material only occurs at such a moving interface. One can derive, like I told you before, by doing an energy balance on the problem. You know what work is being done on the boundaries. You know what is the kinetic energy and potential energy stored in various parts of the bar with a single discontinuity. Once you carry out the analysis of the energy, you can derive what is called a driving force across such a discontinuity, which is given by that expression. W is an expression for the stored energy in terms of the gamma, and these are again quantities all local to the discontinuity. And then the dissipation rate at the discontinuity can be written in terms of the driving force times the speed of the discontinuity. And in continuum mechanics, we want that the dissipation rate is greater than or equal to 0, simply from the second law of thermodynamics. As yet, I have not specified what is the stored energy function that I'm going to use. That comes in now. This is the one. It is stiffening, like we wanted, because we want to look at what happens behind a shock. And for this particular strain energy function, you can do a lot of calculations analytically and arrive at some simple results. That's the stress-strain relation. This is the speed of a discontinuity in terms of the strains ahead and behind it. And C0 is the sonic wave speed. This is basically for very small strains, what is the speed at which the sonic wave is going, and beta 0 is some other constant. You can even obtain explicit expression for the driving force across the discontinuity in terms of the strain ahead and behind the discontinuity. And that driving force will determine which way the discontinuity is going to propagate, because this S dot could be both plus or minus. We always want to make sure Fs dot is greater than 0. So these two expressions together determine the direction of propagation of that shock wave. That is problem one. When problem one is solved for an impact problem where you have a semi-infinite domain with a velocity v applied there, you can go through the mathematics and you can end up with this equation for the speed of the shock wave, which is s dot. That's a cubic equation. You can solve it. It has only one real root. You can show that. And then once you have got that real root, you can compute the gamma minus, the strain behind the shock wave, simply by using the kinematic jump condition. And you can compute the dissipation rate, and it is given by an explicit formula like that. Very good. That was problem 1. It is all related to a continuum 1D problem of a bar. Next, we are going to look at a discrete problem of a mass spring chain, like this one. So this is a mass spring chain. All the masses are of equal mass m, and these springs are all the same. The constitutive law of the spring, the energy stored in the spring, is given by that expression. You can see that it is directly connected to the constitutive law that I used before for the continuum, except I'm writing it in a discrete form now. Delta is the extension of a particular spring. H is the original distance between the two masses. And this is the energy stored in the spring. It has got a cubic term, and it has got a quadratic term just like before. We are going to integrate Newton's equations of motion. So that's the Newton's equation of motion for a particular mass number j. And there is also kinematics which says that the distance between the two springs is changing in a certain way, which depends upon the velocities of the two masses that are connecting the spring. Straightforward. C0, the sonic wave speed, can be written down, which is simply that. Mu here is the constant appearing ahead of the quadratic term here. Okay. So this is, of course, a conservative system. When you integrate the equations of motion, you better find that all the energy that you are inputting at that end is stored as kinetic and potential energy inside the chain of atoms. Okay. So when you integrate the system of equations, what you see is a situation like this. Initially, all the springs are at a distance h from each other. Delta is equal to 0. So this is the initial condition of the string. I've taken a snapshot in time at one particular instant. And what I find here is that there is a front that is propagating into the sample. And there is a large number of very high frequency oscillations behind the sample. Looks like a dispersive shock wave. And then far behind it, the strain is constant, oscillating very little about a certain position. Okay. Same thing, snapshot at a particular atom. I'm plotting the strain history as a function of time, just like I was showing you in one of the earlier slides with the phase transition. Now you can measure what is in their numerical calculations, you can measure what the gamma minus here is, right? And that is plotted as these dots, as these circles in this plot, in the numerical calculations, as a function of the impact velocity, which is non-dimensionalized. And the blue line is the answer that we get from the problem 1, which was the continuum problem. And you can see that they match extremely well. This looks like a dispersive shock wave. The xt plane of it looks like that. There is a leading edge. There is a trailing edge. And the shock wave speed that we computed using the continuum formula in problem 1 lies somewhere between the leading edge speed and the trailing edge speed of the dispersive shock wave. Behind the dispersive shock wave, the strain is gamma minus, which agrees very well with the continuum solution that we calculated before. Very good. So now we want to understand these oscillations a little better. And remember, my focus is on dissipation. So that's what I am going to do next. First, I make sure that the system is, in fact, conserving energy. So the red dots may be the work that I'm doing at the end, and the black circles are the potential and kinetic energy stored in the system. You can see that they're sitting right on top of each other. So once we know that the discrete system is conserving energy, I define two other quantities. Gamma oscillation is the gamma j for the jth spring minus gamma minus. Gamma minus was the solution obtained from the continuum problem, or it is the solution that you see far behind the dispersive shock wave. V oscillation is defined like that in the similar way. And then I compute the energy in the oscillations in a particular manner. Okay, so this is how I compute it. This is the kinetic energy part of the oscillations. This is the potential energy part of the oscillations. And I'm plotting this expression as a function of time in this graph. And you can see that it almost looks like a straight line, which means I can compute a rate, which is the slope of that straight line, and call it the dissipation rate. Okay? And that dissipation rate is here. That dissipation rate is plotted as these magenta circles in that plot. The green line is the dissipation rate that we obtained from the continuum problem. And they sit right on top of each other. Very satisfying. This is the analytical expression that is the green curve. So we are developing some understanding of the oscillations behind this moving shock wave front. And we are indeed finding that these oscillations are going to become heat in the macroscopic description of the problem. Problem 3. Problem 3 now, which is where really the dispersive shock wave analysis is going to come in, is like this. You Taylor expand the discrete equations of motion in problem 2, and that motivates the problem leading up to the DSW. The stress-strain relation is now going to be modified by a term which has got a gradient of strain in it. So this is now a strain gradient type stress-strain relation, which is written up here. And W gamma is the same as before. All other equations, balance of momentum and kinematics, remain the same. You plug this constitutive law now, the new augmented constitutive law with the strain gradient term, into the balance of linear momentum, and out comes that equation, which is the KdV equation. Okay? So once you have that KdV equation, then the machinery of Withum's modulation equations can be used in order to understand what's going on with the dispersive shock waves, what's going on with these oscillations behind the front. Okay, so the way, I mean, this procedure that I'm writing down here is not new to any one of you. It was new to us who have not seen this literature. We looked up the papers of Hofer, and that's how we learned a little bit about this, and then we went about applying those methods to our problem with a little bit of variation. I'm going to tell you what that variation is in a bit. So you say that the gamma xt can be written as g phi. Phi is the traveling wave variable. V is denoted by w phi. You plug all this into the equation of motion upstairs. You get that equation for g prime. The solution of this equation are periodic, and they are given in terms of the elliptic function Cn. And there are some parameters that enter into this solution. There is a g minus, there is a g plus, and there is the m parameter, which determines what is the oscillation frequency of this Cn function. Okay, what do we do about them, about those parameters? You can write various quantities like the speed of the shock wave in terms of the g plus, g minus, and m, and those are summarized here. The group wave velocity can also be written in terms of these parameters. The amplitude of the oscillation is related to that m parameter and g minus, g plus. The average value of g can be written in terms of these three parameters once again, and in terms of the complete elliptic integrals of the first and second kinds. You can notice that this average value of g tends to g minus as m tends to 0. That's the trailing edge of the dispersive shock wave. Tends to g plus, which is the leading edge of the dispersive shock waves. And in our problem, at least in the continuum problem, problem 1 that we solved, these strains, gamma plus and gamma minus, are constants. Okay? And so we are not going to use the full Withum modulation equations, and this is where we are doing something that is slightly different and perhaps may not be agreeable to some of you. We're going to assume that g plus and g minus are constant. Okay? And you will see the justification down the road. And allow only mxt to change as a function of x and t. That's what we are going to do. And the conservation of waves equation is going to be used in order to determine the variation of that mxt. If you assume that this is a scale invariant solution, then you can obtain what the variation of this mxt looks like as a function of x by t because of the scale invariance. And then this is the result that we get. And then we can use that result to do various things. We can write down what the velocity ahead and behind the dispersive shock wave is, and some constants need to be found. There's a little bit of analysis to do here for the particle velocity, And that can be carried out by averaging the kinematic part of the kinematic equation other than the momentum equation. And once you go through all of that, you obtain a jump condition that looks like the Hugonio type jump condition that we were talking about earlier in problem 1. Okay? But the nice surprise is that when you plot the impact velocity v as a function of gamma minus, the plot that I obtained from problem 1 is the red line here. The plot that I obtained from this formula is the green line here, and we have deliberately shifted these such that you can distinguish the two. They are two very different analytical expressions. They don't look similar. You cannot reduce one to the other, but when you plot them, they sit almost right on top of each other. Okay? And this is the xt plane that I showed you earlier. What about dissipation? We're going to get to that. You can plot the DSW solutions. Some plots have been shown here. For comparison, I'm showing you plots of the numerical calculations obtained from my discrete mass spring system, problem 2. Okay? Just like before, I'm going to define my oscillatory strain as either this or this. This is somehow, this should disappear. Let me not attempt it because then I'll mess it up. But gamma oscillation can be written as gamma xt minus gamma minus. Gamma minus, remember, is the strain far behind the dispersive shock wave, which can be obtained from the continuum problem or from the discrete problem. Or you can define gamma oscillatory as gamma xt minus average value of gamma. The average value of gamma is not a constant. It is changing as a function of position. And then after you have all this, the E oscillation can be written in this way using the new augmented strain gradient type constitutive law for the stress and strain. And the average dissipation is obtained by doing this average over from m equal to 0 to m equal to 1, basically from the leading to the trailing edge of the dispersive shock wave. There is no need to go behind because here the strain is constant. Okay, so then we plot that dissipation coming from problem 3 now, and we have two different versions of the gamma oscillatory and V oscillatory, which are written up there. Those appear as either square or circles, and the plot from the continuum formula of problem 1 is this green line that I have shown here. Okay, and once again, we are obtaining some very nice agreement between the two. So this time what we have been able to do then is we have been able to show in a quantitative way that the dissipation that is occurring behind a shock wave in an elastic bar, really all that energy is stored in these oscillations, and you can quantify the dissipation exactly so that you can compute the driving force across the discontinuity, and we know exactly where that energy is going. That's it. We solved two continuum problems, problem 1 and problem 3, and one discrete problem. We showed that the strain behind the shock in problem 1 and problem 2 match extremely well for various impact speeds. The energy in the oscillations of problem 2 matches very well with the dissipation at the shock in problem 2, at the shock in problem 1. That's a typo. The particle velocity jump in terms of strain jump in problem 1 and problem 3 give different analytical expressions. That was the curve that I was showing you, the dashed line and the solid line. But they agree very well with each other if they are plotted. And energy in the DSW oscillations matches quite well with the dissipation in problem 1 over a short range of impact speeds. Thank you very much.
Thank you. Thank you, Prashant. Questions? Karima?
Thank you. I would like to ask a couple of questions just to understand better what you are doing. So in your first problem, do I understand it correctly that you ignore the finite size of the cross-section? You don't have dispersion coming from the boundaries, right?
No.
The first problem is non-dispersive, yeah?
Yes.
Okay. Then in your third problem, you started from your discrete system, yeah, in system 2.
Yeah.
And you added this essentially dispersive term in your potential energy.
Yes.
Which included a parameter h, which is the distance between the particles in your discrete system.
Yes.
Okay?
Yes.
Which is a free parameter in your model.
Yes.
So how do you choose this parameter? Because it seems that, yeah, do you feed this parameter?
Okay, this is a very good question, and your question is answered in the paper that I have pointed out here. what happens is that the eta h square, when you put them together, the value of eta h square really doesn't matter when you compute the energy. It is independent of the energy that is dissipated is independent of that parameter. Because in the solutions, I think somehow these things cancel out. The eta h square cancel out, so the h really doesn't matter. That's what happens.
Okay, thank you. I need to look at your paper to understand that. So another question is, the material that you considered is assumed to be non-linearly elastic.
Yes.
But there is no dissipation,
Yes.
in the material dissipation. So which material do you have in mind?
Okay, difficult question. Think about rubbers. Rubbers are, so the slide that I showed you in the very beginning, the first slide, I mean, this is a fictitious material that we dreamt up because we wanted to understand something in a little bit more quantitative
detail. So that was a theoretical problem, right? You didn't do.
Yeah. But this branch of the stress strain curve for rubber is a stiffening stress strain curve, right? So one can think of such a material as the one that we have in our mind, not with the rest of the curve here where there is first
but
stiffening,
there would be a
softening.
strong dissipation in this material.
Yeah.
So which would need to be accounted for,
Yeah.
right? Okay. And actually, another thing is that when you consider a bar, then there is another dispersion there, which comes from geometry, right? From the finite size of the bar.
Okay.
And this is not here. Yeah?
No.
So this is what we have considered in our problem
Yes.
and our experiments with the bars. So basically, our dispersion is coming from geometry of the bar because it has finite size.
Okay. I'm going to look at your papers.
Yeah,
You've
yeah,
already
yeah.
sent them to me.
Any more questions? First.
I guess a quick question about your H again. So you showed the continuum case and the discrete case, and then you showed that there is very good agreement between the continuum case and the discrete case.
Yeah.
So I suspect that this should depend on H, and if your H becomes sufficiently large, then this agreement should somehow go away. Is that correct?
I agree. So in all my calculations, we have assumed h is equal to 1, and we start computing from there. But it was fortuitous for us that when you look at, so one way to think about it is that how long is your chain? We are thinking of the chain as being 800 particles long, and we simulate up to the time that the shock wave doesn't reach the other boundary, right? So that's thinking of it as you are thinking of a semi-infinite bar. But you're right, if your h becomes very large, then you can start getting problems, and we don't go anywhere near that.
So I thought you were going to talk about the martensite to austenite phase transition, and but another phase transition would be in a polymer, where you get the stretching of the molecules, and you see, and so then you would get a non-monotonic stress-strain relation.
Which molecule did you mention?
Well, I mean, you could have you talked about the martensite to austenite transition.
Yes.
And there you can get a non-monotonic stress-strain.
Yes.
I think you showed a potential which was quartic.
Oh, wait a minute.
Right?
Yes.
So, but in all of your studies, you have a monotonic stress-strain relation.
So
Yeah, that one.
are you talking about this one?
Yeah.
So when we think about austenite-martensite phase transitions, we usually think about an energy landscape which has got multiple wells, right? So this is, in one dimension, the simplest example of a situation where you have multiple wells. And that's the reason why we had used this in many of our calculations when we were thinking about phase transitions and impact-induced phase transitions. But I wanted to understand your question a little bit better. I still don't get it.
Well, it changes the structure of the shocks.
Yes, it does. Well, okay, let me tell you what happens here. So there are no shocks in it, in that particular potential that I talked about. There are phase transition fronts when you go from one well to the other. And I haven't tried to look in detail about what the structure of these things is. In the calculations that I did during my PhD and in subsequent calculations with students, these are usually just 1 or 2 masses wide, not more than that. It's very sharp. Whereas these sonic waves that are going in front, they are spread over a few masses. And
So when you have the phase transition,
Yeah.
I mean, Abiyaratne and Knowles introduced a kinetic relation
Yes.
to distinguish which phase transition you get.
Yes.
That's okay. So I didn't see that in your simulations.
Okay.
Yeah.
It's a good question. So let me tell you now, since you have asked a question about kinetic relations, if you perform a calculation of the type that I did here, you don't have to specify a kinetic relation in the discrete system, and you will get propagation of these phase transition fronts through the median, through the chain of masses and springs. Okay? When you view this problem at the continuum scale, you can write down the driving force across these phase transition fronts in terms of the strain behind and ahead of the phase transition front. From the atomistic calculations, or from these discrete calculations, you know exactly what the speed of these fronts is as well. So these calculations are implying a kinetic relation, and that kinetic relation can be used to solve other problems.
Okay, right. One final remark, and that is
Yes.
that you introduced dissipation very cleverly. You can also have a fourth order dissipation, and I wonder if that can arise from non-local interactions between the particles. And then that again changes the nature of the traveling waves.
Yes.
Yeah. And of course of the dissipative waves
Yes.
as well. Yeah.
It can.
Dispersive waves, I mean.
Yeah. That is something that I only tangentially considered in my thesis work. I can show you something here. So you can see these springs, they are going from this to that. That's a non-local type of an interaction. The overall structure that you get for the solutions of these impact problems does not change. You still get a phase transition front propagating. The details might change a little bit. For example, the dissipation that is occurring at the front might change a little bit. Again, I have not studied that in any detail.
All right. I would say let's break for lunch and come back at 2. Thank you, Prashant.